Okay, we're just ready to begin a fairly short little section on the topic of diffraction. I just want you to take note, please, of diffraction. Please just recognize that this is not the same as refraction. Refraction is something that you will have studied uh, when you've studied light, possibly in year 11, but diffraction is a new phenomenon, something that you have not come across before. We're going to flip over to have a bit of a look at a video here. I found I couldn't really get the audio to come up very well from the YouTube clip, so I might just talk over the top of it. Just a chap here just sort of explaining or just illustrating the formation of diffracted waves. So what he's setting up here is in the middle, he's setting up a narrow slit through which the waves are passed. So you've got plane waves coming through here, and what we see being produced are circular waves there. That phenomenon is called diffraction. All right, so he's making the spacing, the size of this slit, this gap through which the plane waves are passing, making it smaller, and this diffraction effect is more pronounced. The waves are more circular, more curved through doing that. And now he's making the spacing wider, and as he makes the spacing wider, you see that in the middle there's not too much going on, but you still get a bit of curvature at the edges there. Going back to the narrow spacing again. He's saying now he's going to change the frequency and effectively therefore change the wavelength, making the wavelength bigger. And we get quite strong diffraction occurring because the wavelength is quite large relative to the size of this slit, this gap through which the waves are passing. He's now, I think, starting to make the wavelength a bit, so look a bit shorter. Let's see if that's what's happening. He's saying there are two factors here that can affect the amount of diffraction. It's the wavelength of the waves and the size of the barrier through which they're passing. If you'd like to have a look at this YouTube yourself and listen to the commentary properly, I've given you the address down the bottom there. So you could look at it, you could listen to his explanation rather than my attempt at an explanation there. If we have a look at a little animation now, this animation shows the same sort of thing, but you know, being an animation perhaps is a little bit easier to follow what's happening. If you have a look down on the edges here, if you look carefully, you'll see a little bit of curvature of the waves. It's not very, very obvious in that animation there, but there's a slight curvature at the edges. But in the middle part up here, you've basically got plane waves. These lines that are passing along are known as wave fronts. Wave fronts. All right, they're straight or what we call plane wave fronts. If we start to reduce the width of the gap, make it there, let's say, I hope that you can see more pronounced diffraction occurring there and there. And we keep making that separation of the slit smaller and smaller and smaller. We start to get that. Now, I think this animation's got a few limitations. To me, it still looks quite straight in this middle part here, whereas really I would expect with that sort of width gap and that sort of wavelength, I'd expect to be getting something a bit more like that happening. Probably still extending further these ways, but not having this straight bit in the center of the animation. Okay, just flipping back a couple of slides then. In your notes, what I'd like you to do, please, is write the heading diffraction. And then on page 33 of your dictionary, you'll find a definition of the term diffraction. So I want you to write out that definition and then take note of this point here, which basically is saying then that the two factors, the two things that determine how much diffraction is occurring, is then the size of the obstacle or the slit. Now what we've been looking at is waves passing through a slit, but even if they pass an obstacle, we can get diffraction occurring. You'll see this in a later slide. And the other factor that affects the amount of diffraction then is the relative size of the wavelength compared to that. Now, this was diffraction of water waves, but other types of waves diffract as well. So light, electromagnetic radiation diffracts, light diffracts. And you might wonder, why is it then that we do not see in everyday sort of life diffraction of light occurring all over the show? Well, what was the condition? The wavelength had to be similar to the size of the slit. So what sort of wavelengths are we talking about for light? Hopefully you might remember that we're talking of the order of 10 to the negative 7 meters, from about 4 times 10 to the negative 7 up to about 7 by 10 to the negative 7 meters. So you're going to have to pass the light through a very, very narrow slit, to be able to see the effects of diffraction occurring there. All right, just flipping on then to these diagrams. So I want you to complete these diagrams. If you look at your dictionary on the page where you've got the definition of diffraction, you'll also see some diagrams there. But the sort of thing one would expect to see, and I'm just drawing this by hand, I'd like you to do this with a compass. We're seeing these, well, it's not too good just down there, these waves diffracting out. The wavelength here, which is the spacing between these wave fronts, and the wavelength here should remain fixed. So be very careful. Often you'll see diagrams drawn by students showing diffraction, and they automatically make the waves on this side much, much closer together, which is not correct. Okay, and over here, you're going to get this part here coming through pretty unaffected with a bit of curvature at the edges, which is where the diffraction is occurring. Something like that. So I want you to complete that diagram. If you can't find things in your dictionary, have a look at your textbook. And if you're struggling still, have a look up on the web and you'll see all sorts of possible diagrams there. And we mentioned about a barrier. This time it's not a gap, but simply a barrier. This could be a breakwater, for example, trying to protect the yachts in behind. What's going to happen then is you're going to get diffraction behind that breakwater, and similarly over here as well, some sort of diffraction occurring. Okay? So again, taking note of the fact that the wavelength, when you draw it, should not have changed. Two other terms that I just would like you to look up in your dictionary and to write the definitions down. The term coherence. When we're talking about waves, or perhaps maybe light sources, we use the word coherent to describe some light sources. The light that comes out of an ordinary fluorescent fitting or light bulb is not coherent, but the light that we get from something like a laser is coherent light. So I want you to take note of the meaning of the word coherence and also the meaning of the word monochromatic. So both of those you'll find in your dictionary. Actually, I'd just like to pop back for a moment just to talk here a little bit about diffraction again. Just thinking about the sort of situation that occurs with radio waves, because radio waves are an example of electromagnetic waves. Imagine you've got a hill and you've got a radio station here transmitting radio waves. Now, if you're sitting down over here, behind the hill, the radio waves may have trouble reaching you. A lot of it depends upon the particular frequency and therefore the wavelength of the radio waves. If a radio station is transmitting on FM, frequency modulated, then the waves are higher frequency, shorter wavelength. And those waves have trouble, as they travel along, they have trouble diffracting. So they won't reach you over here. You'll be in the shadow. But if instead it was a radio station transmitting on AM, which stands for audio modulated. Sorry, it doesn't. It stands for amplitude modulated, I should say. Then the wavelength for those radio waves is longer, and because the wavelength is longer, those particular waves are able to diffract more. So let's say that's the longer wavelength. They come over here, and they're actually able to get round in behind and fill in the gap. So it's possible to pick up transmission of AM in situations where it would not be possible to directly pick up FM so easily. And in the case of FM, what you'd have to have then is some sort of repeater station up there, which takes the signal and then retransmits it down there to fill in the gaps there. Okay, so this is then the phenomenon of diffraction, which you haven't got too much to write in your notes, but if you can just write those definitions and draw those diagrams, that'd be fantastic. Thank you.